under the umbrella of AI for security. I'm going to talk about one important issue, and that is, okay, hopefully this works. Okay, great. So I'm going to talk about how do you actually support vulnerability analysis based on machine learning. And one critical problem in this domain is, as probably you already know something about, or at least you have been aware of this, the learning-based systems are not like a magic. They have to be fed with a lot of data, right? The model, unlike the traditional program that you write the code line by line, for which actually the code semantics in a deterministic way. You know what the code is supposed to do. At least, I mean, that's what we hope, because you also know that software is buggy, so it's not always doing what you want them to do. But at least, I mean, from the creator's mindset, you have all of these things under your control, and you know what exactly will be actually flowing out of the program. But for learning-based systems, the program is actually not written by developers. They are actually trained from the data. Now, if you want to train a machine learning model to, let's say, identify vulnerabilities, but today I'm going to talk about something broader than just identifying vulnerabilities. I'm actually going to talk about identifying vulnerabilities, checking the presence of vulnerabilities in the code, but also localizing which lines are vulnerable, and also eventually how do you actually repair the vulnerabilities, make the vulnerable code to be healthy again. So all of this will be based on, machine learning, and particularly deep learning. Maybe you're expecting large language models, but today I'm not going to talk about large language models. I'm going to talk about some models that are built on deep neural networks, but they're not necessarily, transformer kind of language models. Oh, but actually we are going to talk about something related to transformers, but they are not like foundational scale models. So in this space, people have proposed all different kinds of techniques for vulnerability analysis, including traditional kind of approaches. So James, do we have some kind of laser pointer to use? If not, that's fine. No? Okay. So traditionally, people actually have static code analysis, dynamic analysis, and one special kind of dynamic analysis is fuzzing. Because dynamic analysis assumes that you already have some test inputs, and then you want to analyze the program as exercised by the existing test inputs. But fuzzing is kind of, complementary to that, trying to generate more test inputs to cover the interesting behavior of the code. So all of them are very successful in different ways. For example, static analysis is very good at comprehensively identifying things. I mean, anything that possibly there in the code. Of course, I'm talking about the ideal world. So static analysis also face a lot of barriers because they may not be able to analyze dynamic constructs of the code. For example, if you feed a static analyzer like CodeQL, anybody use the CodeQL? Yeah, great. So that's actually a pretty widely used kind of a static analyzer for identifying vulnerabilities. But those kind of tools, they are either not like technically sound. For example, CodeQL is actually not even based on the principle, the kind of program analysis technique. They are not solving any analysis problem based on a theoretical model like lattice model, or fixing any fixed point iteration kind of data flow analysis. They are basically querying things from the database. They are modeling the code as some kind of token and some lexicon at most, but they are not really trying to analyze the semantics of the code. And when you query something, they are trying to use some kind of a database querying language to check what you want to know. But they are actually immediately get impeded by the dynamic code constructs in the code. For example, when we say static, we're basically saying the code is just compiled. We usually just call them compile time analysis. So at that point, you're not running the code. You only look at the code. But the thing is, the code you're looking at is not really the code that is executing. Does that make sense? So the code you're looking at is not really the code you're executing. So what you see is not what you get. I'm not talking about code injection attacks. I'm talking about just some of the dynamic language features. For example, the code could be dynamically loaded, or maybe the code is actually encrypted and they're only unpacked at runtime. And sometimes the code is even dynamically changing. For example, JavaScript, JavaScript, you can actually add fields, you can add classes at runtime. So I don't want to get too far into that, but each of these traditional techniques have their critical limitations. So wouldn't it be nice to actually think about different ways? Yeah, they are. So there are some good potentials with at least data-driven approaches. So what we can do is that you can actually look at what has happened in the past, what historic vulnerable code looks like. You're trying to learn the vulnerable code patterns, and hopefully you can use those learned code patterns to identify future things. And similarly for repair, similarly for localization. But the thing is, all of these models are thirsty of data, especially deep learning models. Maybe you're asking, okay, if deep learning models are so thirsty of data, can we just go back to use traditional machine learning? So what is the problem with traditional machine learning? Like not using anything deep, just use a support vector machine, just use random forest. Can we just do that? Yeah, you could do that. The problem is you have to manually engineer the features, right? That's the big problem. Deep learning is very well known for these kind of benefits, which is they allow you to learn the features automatically. You don't have to manually engineer the features, which is actually a very tedious thing. And also, the manually engineered features may not be really good at capturing what the concept is, what the data objects is. So we want to use deep learning, but deep learning is thirsty of data, and the existing data sets have the following problems. Many of the currently used data sets are synthetic, totally synthetic. I mean, that's fine. Synthetic is not being synthetic itself is not a thing. It's not a thing. It's good. It's actually useful. But the problem is they are not only synthetic, but they are not realistic. So when we say the data set is synthetic, we are saying the data set is generated. It is computer generated, not like a manually created, not like produced from a developer's code in real world scenarios. So that's what we consider synthetic. But you can make synthetic realistic, or you can make synthetic very trivial, right? For example, some of the widely used data sets, like a SAR data set, some of you who worked on vulnerability analysis, you definitely know this data set, SARD. So that is a data set curated by humans, but they are totally artificial. They are created by humans, but not from real world software projects. So the code is very trivial, and they are artificially made certain ways to make them kind of cover different kinds of vulnerabilities, but they're not representing real world scenarios of how vulnerabilities should happen. So the other problem is there are real world data sets, but they're too small. They're not enough to crank the engine. If you want to crank the engine of deep learning models, you need enough gas, but you don't have enough gas, they cannot be cranked, right? They cannot start it. It can't be started. And as a result, many of the evaluation results today you are seeing are highly inflated. They report very promising results, but their results are based on not very good basis. You may not be able to trust the results. I mean, a lot of papers report their vulnerability detection technique can get 90%, 95% accuracy. Would you trust that? Obviously not. I mean, if that's true, then the problem is solved. It's almost solved. So what we want is we want to generate the data set. Okay, I'm spending a bit more time on the motivation part. I'm going to spend relatively much less time on the technical details because I don't expect everybody is actually so interested in the technical details. If you are, you can definitely check out the paper. My job here is to kind of give you some kind of educational material about these projects, backdrop. So why we are working on this, and what is the significance of this problem, and what is the high-level methodological ideas behind the solution. So yeah, we have looked at several possible ways. So what we want to do is that we look at some potential ways to solve this problem. How do we get the data set? Well, certainly you can collect the data from wild. For example, you can go to GitHub. I mean, developers make a lot of commits to fix vulnerabilities, right? But developers are not always doing the good job of documenting what they are doing. So for example, they made a code change, they push the commits to the repository, and the code commits are supposed to fix vulnerability, but they don't say so. And without that clue, you may not be able to automatically collect all of the vulnerability fixes. I mean, if you are able to do that, you could just reverse. Today we have talked about the word reverse third time. So my slides was reversed. So this time you can reverse the vulnerability fixing commits to make them vulnerability injection commits. So for those who are not quite familiar with this domain, what we are looking at is the problem of faulty injection problem. So faulty injection has a lot of applications. So if you want to really validate the robustness, the capability of your technique, and you don't have so much like faulty data set, because if you wait until the real world faulty situations happen, that may be too late. I mean, this is like really like the attack and defense mindset. In the security community, people keep publishing papers on attacks. I mean, why do they actually propose attack strategies? Well, that's because they want to get to know about the possible attacks before the real attackers launch the attacks. So here's the same problem, right? If you want to make your software to really help with spotting the real, faults, you want to test your software by, running them against injected faults. So we don't have so many scenarios of the faulty problem and like the faulty scenarios, but you can create those faulty scenarios to, to test your technique more adequately. So that's the same idea. We want to get a vulnerability data set. Okay, that's a problem. Because we don't have enough data set to train the model, but we are not so much interested in creating the normal code, because we assume that the majority of the code you can find from the wild is normal. I mean, until anybody found any zero-day vulnerabilities, we assume they are normal. So you can get plenty of them. You don't need you don't need to create. You don't need to worry about the lack of data set in that regard. What we are really lacking is the vulnerable code that are labeled as so. Okay, so we want to get those kind of samples. So that's the problem. And the idea is that can we inject the known vulnerability code patterns into the normal code so that we can generate more normal code? Oh, we are doing evil things because we are generating vulnerable code, but don't worry. So this comes to the ethical problem. So every time you write a security paper, you have to talk about the ethics. Otherwise, your paper will be rejected. That's rejected because you have to be responsible for whatever kind of security problems you found. You are the first one who discovered this security problem, and that problem can become, the point of attack from, the adversarial mindset. So that's why you have to do something to make sure that you don't leave opportunities for the evil guys to do the evil things. So here we are generating vulnerable code for good. We generate vulnerable code, but we don't really inject this vulnerability into real world, serious software systems. And more importantly, we don't publish the exploits. So we don't publish the exploits. If you don't have the exploits, only know the vulnerable code patterns, it's not going to do much harm to the community or to the healthcare of cyberspace. So we have already taken care of the ethical concerns. And the idea is that we want to generate the vulnerable code by injecting existing known vulnerable code patterns into the normal code. So that's the whole idea. That's the high-level methodology. And one way to go about doing that is that let's learn the vulnerable code patterns. And then we build a deep learning model to inject the code patterns into normal code. Can we do that? Yeah, you may be able to do that. But do you think we are actually hitting a chicken egg problem? A chicken egg problem. it looks like my computer is attacked. It's being attacked because I'm injecting vulnerabilities to the system. Okay, it's back. So yeah, we are kind of facing the chicken egg problem because on the one hand, the purpose of doing this project is to create more vulnerable code that are labeled as so in order to empower the deep learning based vulnerability analysis technique. But now you're asking me to build a deep learning model. Then how can we get those kind of enough data to train this model in the first place? Right? That's the chicken egg problem. So please think about who is chicken, who is egg. So think about that. So, but we definitely have a chicken egg problem. So we come up with this kind of idea of combining a traditional approach that is based on pattern mining and a deep learning approach. So we cannot entirely avoid using deep learning because deep learning is still useful because they are good at capturing the code patterns. At least that avoid human efforts to manually, create those patterns. And so what we are doing is, let's use deep learning to only learn this relatively simpler things. So think about how do you inject vulnerability into a normal code? Pretty much like a bug injection. If you want to inject a bug to a non-buggy code, what do you do? First of all, you need to do localization. So I want to give a talk today, but first of all, I need to get here. I need to get the right place. So you need to first find the right location for the injection. And then after that, you think about how do you make the code changes at that spot, right? Do you agree? So conceptually, you can decompose this problem into two sub-problems. First, locate where you want to change. Second, make the changes you want to make the code vulnerable, right? And our idea is that use deep learning to only learn the location, but use a pattern mining technique to make the changes. Why is that? Because intuitively, only predicting where to change, in other words, only to know where to change rather than knowing how to exactly change, is much simpler than knowing how to change it. Okay, so basically you just need to identify the context. So if given the piece of code, you have the control flow structure, just tell me where I should change without caring about how to change. So that problem is much simpler, and intuitively, if you train a deep learning model to do that task, it should require much less data. Okay, that's the key insight here. But for the real changing part, we are going to use an AST-based edit pattern representation to represent how code can be changed from one version to another. So I actually have some examples, I believe. So do I have code change patterns? Okay, I may not have that example here. So let me see. Okay, this is about localization. Okay, I still believe I may have some examples of that. Yeah, these are a lot of patterns here, but I know it's very hard to see, probably it's very hard to see. It's not so clear. So the pattern basically includes okay, this is one example of pattern. Hopefully you can see some of this, right? So basically the pattern is represented as some kind of a placeholders like a wildcard, some kind of thing to represent the variables, but you only keep the skeleton of the code, like the syntactic structure of the code, but basically symbolize or like abstract the concrete variable names or any identifier names. And after you do that, you can use a technique called anti-unification to generate the more general patterns that can represent that can basically summarize all of the concrete edit patterns. So that's how you represent the edits. Yeah, again, as I said, the technical details are not so important. My job is here to give you the background information and also hopefully convince you that this is an interesting problem so that you can actually maybe follow up by reading the paper itself. So what we do is that for the actual change we want to make, we use the edit patterns, because the edit pattern has two parts, left-hand side and the right-hand side. It exactly tells you how to change from the left to the right. So that's like a fully deterministic approach, nothing probabilistic anymore. But that's the most difficult part. That would require much more data sets to train the model. So we combine deep learning and pattern mining. Deep learning to learn the localization. And this is a high-level idea. So we use deep learning to learn the localization. And then we use the patterns to help you inject the code, inject the vulnerability. And more specifically, what we do is we start with a very small existing vulnerability fixes, because these fixes actually tell me how vulnerability is actually injected into the code. Because developers make the fixes, but if I reverse the fix, I would know how the vulnerability was actually injected. For example, if the vulnerability fix is about adding a boundary check, then I can just remove the boundary check. That's how I inject vulnerability, right? Does that make sense? So it's very intuitively to understand that kind of idea. And with that, we perform some kind of pre-processing. When you develop a deep learning model on source code, usually you have to do something called tokenization. You want to remove some of the things that are not really essential. So you want to, at least you want to split the code into individual tokens. So it's a tokenization. But oftentimes the people these days also do something like subword tokenization to actually try to avoid out of vocabulary problem. So that idea is basically, even for individual token, let's cut them out. Let's cut them into parts so that you have more chance to cover all of the vocabularies in your code. You have more chance to cover all of the vulnerabilities in your training data set compared to the potential testing data set. So we do all of that, but now we want to be able to predict the vulnerability injection location more precisely. We want to teach the model to learn something about code semantics. And one idea to learn the code semantics with respect to the injection location is we propose this kind of what we call the value flow based localization learning. And the idea is this: we are trying to pre-train a transformer model. So the default transformer model is already there. So they have the position encoding. They have the position encoding is basically designed towards capturing the natural language, vocabulary kind of semantics. For example, if I say, I'm coming to Todd Hall to give a talk. So if you look at this sentence, some of the words are bonded together much closer than others, right? So talk, probably these two words should pay attention to each other more than to, going to. I mean, those words are probably not the most essential word for capturing the meaning of this word. So I'm just trying to give you this basic, the intuition why, kind of customizing the position encoding in transformers is something that is useful to do. Because we want to do localization. We want to learn somehow, where is the right place to inject the vulnerability. So the location matters, but how do I know the location, which location is more interesting? Okay, first of all, in my training data set, okay, the training data set comes from here. This is the training data set. In this training data set, I already know existing vulnerabilities injection location. Again, let me emphasize this one more time. even though I'm looking at this data set for training this model, but I'm not using the actual code changes. I'm only using the information about the location because I'm training the localization model. So from the existing vulnerabilities, I know which places in code are interesting for vulnerability injection. Okay, that makes sense? So that's basically what you already know. I mean, that really comes back to the general idea of machine learning in general. So you need to know something that is called ground truth. You know the ground truth. You know what is actually, vulnerable. Which locations are actually vulnerable. So you teach the model trying to learn to pay attention to the more vulnerable places or the more suitable places for vulnerability to be injected. So using those locations to train this transformer so that we hope the transformer can learn those patterns of the code locations that can be injected with vulnerabilities. I mean, I think we need to invest more in cybersecurity today, right? Okay, so, but remember, this data set is very small. Make sure I'm not running over time. So remember, this data set is very small. How can we learn a useful model based on such a small data set? It's hard. So for example, this one may only have 1,000 samples, let's say 1,000. We spend a lot of hours manually labeling this kind of training data set here, but this is not enough to train a very large model. So even though this transformer, so here, by the way, we are using a particular code transformer called code T5. So code T5 is inheriting the same kind of a model architecture from a model called T5. So T5 is a model designed for natural language processing. But then people train the T5 architecture on code. And that's how they get code T5. So this kind of model, they are trained using self-supervised learning. They're not using labeled data set. They are using, basically the model is trained in a self-supervised way. For example, you have the data. I'm going to remove certain tokens, and then I'm training the model to find the tokens back. Okay. One of the most well-known kind of a self-supervised learning objective is massive language models. So like token prediction, missing token prediction. I purposely remove. So give me a document. I know what the tokens are, right? All of the tokens are, I know them, but I try to remove some of them, and then I try to train the model to learn the token, try to predict the token that are removed. So in this way, you don't have to do any labeling. Does that make sense? So basically, we are trying to use this kind of a self-supervised learning objective to train the model, and so that the model can learn more about the data set. So here, what we do is that we also utilize pre-training, but we want to design pre-training objectives that teach the model to do something that is relevant to our downstream tasks. Our downstream task is to learn the localization of vulnerability injection, to learn where to inject vulnerabilities, and to make the model to learn some general knowledge for that task. One thing we can do is that let's remove irrelevant statements and then try to teach the model to find back those irrelevant statements. When I say irrelevant, I mean the statements that are not relevant to any vulnerabilities in the code. So, but the labeling which statements are irrelevant or not also requires manual effort or some kind of labeling effort. So we don't like it. So that's not a self-supervised objective. So then what we do is that we just remove any statements. We just remove randomly selected statements from the program source code. And then we try to use the transformer to learn to generate the missing statements. So we use those kind of a pre-training objective to pre-train this model before we fine-tune the model on this small task-specific data set. So by the way, I need to emphasize what we are really doing here. So we use the data set in the wild. I mean, I just need a source code. For any source code I grab from the, for example, GitHub, I don't need to know any label about the code. For any code I grabbed, I just remove randomly some of the statements. And the learning objective is to find back those missing statements. That's it. So in this way, I can use an enormous amount of data to train my model, to pre-train my model. The purpose of doing this is to make the model more sensitive to, code locations. Because when we say code locations, we are basically talking about the statements. So some statements are removed. I'm trying to learn them, learn to find them back. When model is trained on this kind of tasks, the model becomes much more sensitive to locations. So that's what. So, but we also have some other. Oh, really? Do we have a man in the middle attack? So, who is that man? So we also have some other pre-training objectives. We have some. So we have 3 pre-training objectives to help the model to learn the localization. Another pre-training objective we use is use AST to predict the code. Basically, I have a bunch of AST, and then I have a bunch of code. Tell me which AST corresponds to which code. So basically, that's the idea of try to teach the model to identify, syntactic structures of code. So in the training, of course, I give the model some ground truth about, okay, this is my code, this is my AST. I give you the paired data set to train, but then I hope the model to learn the correspondence between the AST structure and the source code. And after that, okay, yeah.
Could you briefly explain what an abstract syntax tree is?
Oh,
Maybe some people would know.
Yeah, okay. Yes, so I think that's a good reminder. I saw that all of you are my cybersecurity class students. Yeah, AST, abstract syntax tree. So, I think this is good because we actually have some examples. So if you give me a piece of source code, unfortunately I'm not showing the source code. I don't think I shown the source code, but this is what an AST looks like. So what you do is that programming languages, they have their syntax. You have to follow the syntax. For example, if you say English, you have to follow English grammar. That's what we call syntax in programming language. And the idea is that in order to make the sentence meaningful, I wouldn't say even meaningful, to make the sentence legal, to make the sentence really valid, you have to follow certain rules, like which word should appear before which word. Which word cannot jump ahead of the other word. Basically, it's about the order of the words, and also what kind of words are legitimate. So, for example, we don't have XYZ as an English word. That's not a valid token. So basically, syntax defines something beyond that. So we have 2 things to differentiate: syntax and lexicon. So lexicon basically defines what are the meaningful words that are acceptable. But syntax defines the structure, the ordering of the tokens, how the tokens should be organized to be meaningful, right? So in order to represent that kind of a syntactic, feature, we can actually break the source code into individual tokens, and then we use the tree to represent syntactic structures. For example, this is a statement. For example, A equal to B. You can actually break this into 3 tokens: A, equal sign, and B. And this is a statement, and this statement includes 3 nodes. And these 3 nodes become the sub nodes, or like you can generally define them as subtrees. But if you think this in a more general manner, you can actually represent a much bigger source code also in this kind of tree structure. For example, if you have a for loop. So a for loop in program language is considered one statement. That's a compound statement. So, but you can actually represent the for loop, that statement itself, like where you define the loop variable and the loop conditions. You can use one statement to represent that. But then all of the statement in the body of the loop, they also a lot of statements. Then you can represent the whole for statement as a tree. So yeah, so basically all of the leaf nodes, the terminal nodes, are the unbreakable tokens. And then put them together into some expressions, into some conditional expressions or arithmetic expressions, and then into an even higher level syntactic structure, and finally into the whole program. So that's how you can form the syntactic structure of the code in your tree. Hopefully that makes sense. Yeah, okay. Thanks for that reminder. Yeah, so I forgot to give that a background. So, okay, let me get back to the high level idea of learning the model. We use those pre-training objectives. So for those who are not very familiar with model pre-training, again, I can give you an intuitive analogy, which is if you want to teach a child to do a particular task, for example, drawing some kind of picture or something, that's a more like advanced task. Before you teach the child to do that, you probably want to teach the child to do something relevant to drawing. For example, maybe just drawing anything. Okay, let them drawing anything on a board without any meaning, just to exercise their arms and just to exercise the flexibility of their hands. So that task is not going to help you address the particular task of drawing, but that task build up towards that kind of task, right? So instead of, okay, if you want to teach the child to draw pictures, some other tasks are totally irrelevant. For example, you teach the child to, you just keep, playing some music to the child. I mean, that's not going to help. But you want to use some tasks that are relevant to the ultimate task to help the model to learn some like element, like a rudimentary kind of subtasks, some of the relevant knowledge that is going to help the model eventually learn the downstream task. But more technically, what this means is that we want to warm up the model's weights, because when we train a deep learning model, what you are trying to do, because deep learning model essentially is a high dimensional function function approximator, right? It's a high dimensional function. And these functions variables are basically the features, but you also have a lot of weights to connect the features together. So doing pre-training is kind of warming up the model towards initializing the model's weights towards some directions, or in more technical terms, gradients that are closer to the ultimate task objectives. So that's the purpose of pre-training. I don't think it's realistic to cover all of these things to make you fully understand everything in this particular talk, in this particular work. Actually, that's not very important for this workshop, because you guys will also learn many other exciting topics given by other speakers. But for this one, I just hope that you can get the high level idea of what we are doing here and what are the possible ways to go about doing that. So here, we just try to learn this localization model to make the model to be more ready to do the ultimate task of localizing where to inject vulnerabilities, okay? So that's one thing we do to pre-train the model. Another thing we do, I only have a few minutes, I need to go over it quickly. The other thing we do is we customize the position encoding in transformers to make sure the position is computed not based on natural language meanings, but based on code relationships. And here we define the code relationship through value flow relationship. What do we mean by value flow? I also have some examples here. Value flow basically means, okay, I have a value here, password, and this value flows to this place because it's defined here and it's used here. So value flow relationship essentially is a data dependency relationship. Okay, where you define the variable and then where you use the variable. Because where you use is impacted by where you define it, right? Because immediately this value here is determined by value here. So we use this kind of relationship to calculate the position encoding within transformers. So I know this probably requires some deeper knowledge about transformer internal architecture, but basically we want to incorporate the positions. Definitely, I don't want you to look at this equation. You don't need to do, okay? So basically, but this is how we actually change the model internal architecture to make the code to learn where to inject vulnerabilities. After all of this, once the model learned the localization, okay, getting back to high level picture, once the model learned the localization, we will be able to actually make the changes at that location by utilizing the suitable edit patterns at that place. Okay, we have a bunch of edit patterns we prepared in advance, and given the location is predicted for injecting vulnerabilities, we will calculate the fitness of that location with the edit pattern and see which patterns are suitable for that location. Okay, and that's how you inject the vulnerabilities. So let me jump to the results. Let me give you all of the details. So finally, so our technique is called the VGX. That's called vulnerability generation enhanced. So X stands for enhancement, and VG represents vulnerability generation. So what we do is that we compare our technique with several other relevant techniques, and what we do is we generate vulnerabilities. And our results show that we can generate a variety of vulnerabilities in terms of CWEs. Everybody knows what CWE is, right? So that's basically the different kinds of vulnerabilities, like a buffer overflow divided by 0. There are different classes of vulnerabilities, and we use CWE to represent to basically encode those kind of classes. And we can actually generate very different kinds of vulnerabilities. And in total, we were able to generate 150,000 samples. And in that 150,000, the success rate is 90%. So which means of all of the generated samples, 90% are actually vulnerable. So the label is correct. So that's really important. Yeah.
What is the scale on the left-hand side of that chart I used to?
Oh, this scale? Oh, this is the number of samples we have for each CWE.
But that doesn't, I mean, that looks too low to add up to 150,000.
Right, that's a very good question, because we ultimately, we just sample out of this 150,000, we sample 10% of them. And out of those 10%, we manually look at, whether the CWE is also right. Yeah, that's a good point, good observation. And by the way, if you want to use this kind of generated data set to augment, okay, now we are getting to the point of data augmentation. Looks like my time is running out. So we add the vulnerable code samples to the existing deep learning based vulnerability detection model to basically augment the training data sets. However, if you want to augment an existing training data set, you want to be very careful. You don't want to change the balance, because maybe the model. So then if you want to add 100, so let's say originally the training data set is 10% vulnerable, 90% negative, which means they're normal. Now, if you want to augment that training data set, if you add 100 vulnerable samples, then how many normal samples you also should add? You should add 900, right? In order to keep the original balance, you want to add the proportional number of normal samples. Now, if we want to add all of those 150,000, you would have to add 1.5 million normal samples. Something like that. That's too many. So we can definitely collect that many normal samples, but the model training will take a long time. So that's why we don't have that kind of resource. That's why we only sample 10% of that to add that to the existing deep learning models. You don't have to understand all these numbers, but basically the conclusion is by adding these generated samples to the existing deep learning models, the model's performance boosts a lot. So that's the goal we want to see. And more interestingly, using an existing previously trained model to detect the vulnerabilities in Linux kernel, they can detect some, but not all of them. And now using our data set to enhance, to augment, okay, that deep learning based model, we were able to detect, how many more? I think I have that number. These are all the additional vulnerabilities. I think we were able to detect 13 more Linux kernel CVEs. So these CVEs are already reported and confirmed, but these CVEs were not able to capture by the original model. But once you augment the model with more training data set, they are able to capture more. So that's basically conclude my presentation here. I hope that you learned something at least. Of course, many of the details are basically just skipped, but I hope those skipped details are probably what you're least interested in. So, but if you do want to know more, definitely reach out to me offline, and also you can check out the paper. The paper is called VGX. Yeah. Okay, so thanks everyone for bearing with me. I'm not sure whether everybody's actually super interested in this, but I hope you at least know this kind of problem is there and what we can possibly do to at least mitigate. I'm not saying that we are solving this problem entirely, but at least we try to improve the situation. Yeah. Thanks again. Yeah.
Thank you very much.